Good morning. It's my great pleasure to be here today on behalf of my co-authors, John Baez, co-author and co-presenter Xiaoyan Li, to share with you our work on ModelCollab, software to empower diverse stakeholders across the interdisciplinary modeling teams that inevitably lie behind impactful public healthcare modeling projects. Now, this work has been shaped and made possible by many. I'd like to single out Xiaoyan Li for putting in place StockFlow.jl, but also Eric Redekop as the primary architect, designer, and implementer behind ModelCollab itself. But also Sophie Lipkin and Evan Patterson, and of course John Baez, who put in place the conceptual foundation, mathematical foundation for this work, and Alex Allegro and Thomas Purdy, who hail, like Xiaoyan and myself, from our Computational Epidemiology and Public Health Informatics lab at the University of Saskatchewan, where I hold an appointment in computer science, as well as one in community health and epi. Now, the motivation for this work lies in the 25 years of my life that I've dedicated to improving decision-making in public health, healthcare, and community safety and well-being. Now, this work has brought our lab in close working relationships with a wide variety of health system partners, from the local to regional, provincial, state level, up to the federal levels in Canada, in the US, and in Australia. And one of the big realizations that's come from that work is that when it comes to impactful modeling projects, really it's teams, not individuals, individual modelers, are the units of success. Very commonly, and almost inevitably, impactful modeling projects involve stakeholders from a diverse area of backgrounds. General practitioners as physicians, to be sure, but often public health officers, such as medical health officers in Canada, the frontline folks in public health, epidemiologists, but often allied health professionals like nursing or social work, folks from veterinary sciences for diseases across the animal-human interface, but also specialist physicians in areas like infectious disease, critical care, and emergency medicine. And really a huge factor in the success of these projects consists in realizing their potential, consists of the degree to which you can reach out to and effectively leverage the shared understanding of members of that team. There's a key need to build a model that captures an external situation well, say the spread of COVID-19 in the community. One needs these interdisciplinary team members to be able to challenge, to critique, and help evolve model assumptions. And to do that, they need to understand what's represented in model structure and be able to challenge that, but also be able to run the model and challenge its behavior over time. Now, not only is that needed for building an effective model, but for securing buy-in, securing trust, and a sense of ownership by those individuals. So we routinely, in support of this, like many other modeling teams, particularly in the system dynamics areas, engage in participatory modeling, where the models themselves, the diagrams for the models, form boundary objects, these shared elements of the social space of people from very different backgrounds that actually aid communication. To support this in system dynamics, we use three major types of diagrams, which are well codified in the literature, although not previously described as mathematical constructs themselves. These include causal loop diagrams, system structure diagrams, and stock and flow diagrams. As one goes goes down the page. There's a matter of successive elaboration and elucidation, sharpening of distinctions, and also the richness with which one uses the diagram to understand behaviors in the world. While there's a variety of types of traditional system dynamic software, tools like VenSim and PowerSim and iThink and Stella, AnyLogic, they fall grievously short in supporting the sort of interdisciplinary team-based modeling. All too often, they treat these different diagrams as solitudes to one another, inevitably. There's no mapping between them. Without an understanding of their mathematical structure, they're treated as simply alternative descriptions of a situation with no relationship captured. More fundamentally, there's a lack of model modularity or any sort of capacity for composition. Higher levels of abstraction for molecules or archetypes are recognized, but can't be composed. There's an inability to express relationships between these diagram types, but also a failure to support the teams whose knowledge is central to success, and sort of odd decades-long privileging of a single user interface. There's also just one size fits all in terms of model output rather than model output geared towards particular stakeholders, and an inability to combine these models with effective computational statistics or to effectively stratify them. Now, for this reason, we've introduced this ModelCollab, and within this area, I'd like to turn to this interface and ModelCollab.use.ca, and we're going to be adding in a model. It's one of the two types of models shown. In this case, it'll be a stock and flow model. And I'm going to be, we're going to be working on this canvas here. And we have a palette by which we can draw the building blocks associated with stock and flow models. Now, one of the first things you'll notice is that this is a real-time collaborative interface, sort of like a Google Docs for modeling. And is almost unique in that regard. And we're going to be focusing, while Xiaoyan builds out certain components of the model, we're going to be focusing on components associated with the spread of infection. So I'm going to draw these stocks represent compartments or accumulations of people. We're going to draw one for new infections, but to calculate that, there'll be a rather articulated calculation that is needed, and we'll be using the space above for that purpose. Now, to support that calculation, we'll need both some assumptions in the model, assumptions that can be varied across different scenarios, one of which will be the total population. We'll be setting that to 1.2 million here. And there'll be a number of contacts per day that a given susceptible makes with anyone in the population. Now, this number of contacts per day is made on a per susceptible basis. And what's going to affect the risk conferred or imposed on a given susceptible will not just be the number of contacts they have per day, but the number of discordant contacts, contacts with infectives that they have. So I'm going to go introduce a variable called discordant contacts per day. And you may note that this looks a little bit confusingly like a parameter, but you'll notice its icon is actually different. It's a V shape here. In order to calculate it, we're going to need to use an approximation that's long been part since the days of Kermick and McKendrick in the late 1920s. of the dynamic modeling toolkit. Specifically, we're going to reason about the fraction of their contacts per day that are infective by calculating the fraction or prevalence of infectives within the overall population. This, again, is a dynamic variable. It's an auxiliary variable endogenous to the model and calculated as the model evolves. The prevalence of infection, as well as the discordant contacts per day, are domain-facing quantities to help make the model more transparent to domain stakeholders, both by allowing them to reason through the causal structure of the model, the equations that underlie it, and in order to get output from them, although this is under-supported by ModelCollab right now. It is something we can examine within StockFlow. So there'll be a formula for the prevalence of infection given by the number of infectives in the population divided by the total population. Within this model, E represents individuals who are latently infected. They're infected, but not yet infective, and we're calculating the prevalence of infectivity. Now, having calculated the fraction of the entire population that's infective, we can now create an approximation for the number of discordant contacts per day that a susceptible will encounter. And this will be given by the contacts per day times the prevalence of infectives here, of infectives. Oops, excuse me. Contacts per day times prevalence of infectives. Okay. Great. Now, to complete the picture in terms of the risk to a given susceptible, we're going to take into account one other key parameter, the transmission probability. That's the probability per discordant contact, per contact between a susceptible and infective, that infection will be transmitted. And this, like contacts per day, will be given a value. In this case, it's going to be 0.1. And using these values of the discordant contacts per day, the contacts that a susceptible makes with anyone, with an infective, and the transmission probability, we can use that to calculate what mathematical epidemiologists and those in public health refer to as the force of infection. This probability per day, the temporal probability, a hazard rate, that a given susceptible will get infected. And the force of infection will be given by the transmission probability times the discordant contacts per day here. Okay. And to speed this up a little bit, I'm going to just copy this formula. You'll forgive me. From my previous rendition of this model. Okay. And we'll do the last little bit of firming up this model structure, calculating the number of new infectives as susceptible times the force of infection. Yeah. Okay, great. I think Xiaoyan already put it in there. Great. Xiaoyan has also gone and populated each of these stocks with initial values. And she's made the common assumption that the residence time in any given stock is exponentially distributed with a time constant as given by the respective quantities for each of these stocks. And there's a waning of immunity that occurs after an immune period that by default, the default value for the baseline scenario will be 270. Okay. Now, having defined the model in this way, there are several things we can do. One to which we'll come back is we can go get the code of the model. Often this will be of interest because for more power users, they may wish to use it directly in the context of stockflow.jl. But I want to run the model, but to do that, I need to create a baseline scenario for the model. I need to have at least one scenario, and I could easily create alternatives. There's only time to allow us to define a baseline here. We will add that baseline, select it, and you notice that as a scenario, we could set the time horizon for simulation, as well as the parameter assumptions to be used for the model. Now, having defined this scenario, we can go select it as the current scenario to be run, and I'm going to run the model. While I'm doing that, I'd like to draw your attention back to the code that was exported from this model. And specifically, darn it, to this code. So you'll notice this code makes use of a domain-specific language, using one of 5 supported in stockflow.jl, which is used to define a stockflow model consisting of a declarative characterization using Julia macros of the stocks of the model, the parameters of the model, the dynamic variables of the model, or auxiliary variables, and the flows of the model. Now, having defined this in this way within the Julia code, in this declarative fashion, we can do many things with it, and we'll be seeing them in just a minute here. But first, I want to go back and see if we can see some model output. And so far, the model is finished running, but I'm not seeing any model output. So I'm going to go run it again. And we'll see if so back to this, this file here, this file does provide a way to bring the model through to simulation. The model outputs are now produced by the system. You'll notice a rise in the number of infective individuals and a decrease. The number of susceptibles is falling, and the number of recovereds is growing with the characteristic oscillation reflecting loss of immunity. However, building up a model like this, we can do a lot more than just simulating it in isolation. After all, this model is described by data. This model, ModelCollab, rests squarely on stockflow.jl, which uses co-presheaves or C-sets, or more technically attributed C-sets or atchets, to encode model structure. So we have a category in which we have as objects stocks, flows, parameters, dynamic variables. And in the co-presheaf, those are mapped over to FinSet. And so we have some number of stocks here. We have some set of flows. And we're encoding here in a database fashion that database instance characterized by the C-set. There's some of these relations are monomorphisms, for example, from inflows to flows and outflows to flows. But fundamentally, we're describing the structure of this model as data. And as data, we can do many useful things with it. Within stockflow.jl, using that code we looked at, there's particularly many things we could do. We could stratify the model. We could compose it. We could go map it to different semantic domains, extract a particularly simple form of causal loop diagram. Here in ModelCollab, we have smaller repertoire, but still an important one. And one of the most important things we can do is import a model. So we're going to import a model here, model B, which characterizes a process besides the infection spread process, a process associated with vaccination. And in order to make use of this information, we are going to in order to, so right now it's a simple co-product of these two models. In order to compose them, to glue them together, we have to specify in a structured co-span type sense what variables we wish to identify. And there's two of them. The first that I'm going to be doing will be identifying stocks with stocks. So we're going to identify the S variable here, the S stock in the imported model with the S stock here. And I'll be taking their push out. Xiaoyan will meanwhile unify total population in the imported model with total population in the model above. So to do this, I'm going to use this identify icon, and I'm going to identify the two stocks. Xiaoyan, I could see, has already identified the total population variable. And now we have this this composed structure. Now, in this context, we could get the code for this combined model, but we will need to, before we can run it, select the baseline. I want to show you that with this model, we have not only the original model, but we have the imported model. And then there's a characterization using structured co-spans as to how to compose them. And again, there's a domain-specific language that was designed by our group to help make that composition easier to understand. So here we're composing around S, for example, identifying it between the two models. Now, it's a somewhat hideous visual representation right now. By jiggling it around, you can sometimes make it a bit less ugly, but we have a lot of work to do to make composed models appear well laid out. But we're still not done with our importing. We imported a model and unified it with this one to capture the effects of vaccination. We're now going to capture the effects of asymptomatic individuals within the model. And for simplicity here, although it runs counter to how we handled them within our actual work, we'll treat them as conferring no risk of transmission. In reality, they're commonly viewed as associated with a risk more comparable to regular individuals. So here, I'm going to again unify E with E, and I'm going to unify R with R. And now we have an asymptomatic infection pathway, if a somewhat awkwardly shown one. And once again, the code for this model could be examined. And one thing one would find is that there are now 3 models here. The original model, the so-called outer model, this model with asymptomatic infection, with vaccination, and they're pieced together using this domain-specific language. Finally, we will go and edit the scenarios. You'll notice that the scenarios now include assumptions regarding these imported pieces, which are now modularly glued together with elements of our model. And we will, having inspected those scenarios, go and select one, and we will seek to run this model. And it may take a bit of time to run this composed model, but hopefully we'll be able to see the dynamics of this entire composed complex of models that's a result of this combination. Okay, having seen this, I'm just going to make some final remarks here. So what we've seen is support of a platform, ModelCollab, made possible by this theoretical work undertaken jointly with John Baez and Evan Patterson and Sophie Libkin, with Xiaoyan also playing an important role. But also building on real-time collaborative software design, use of the operational transformer technique in human-computer interfaces for real-time collaboration, and drawing on a group who built up domain-specific languages, etc. Okay, so this failed to run, so I'm going to restart it. It is an approach that allows for diagram-centric modeling in the tradition of system dynamics, but in a way that supports modular diagram-centric modeling, composing together diagrams and swapping out one representation for another in a way that affords reproducibility and affords easier experimentation. We can share and reuse libraries of diagrams such as those previously published. And we can, through this separation of concerns via modularity, we can divide up work among a broader team. There's a separation of syntax from semantics. Our current use of that in ModelCollab is quite limited. But within this summer, we'll be adding these mappings. We're planning between diagram types, as well as several types of semantics for these diagrams, such as those associated with identifying polarities for different pathways. And this is real-time collaborative user interface. And we're seeking to move towards semantic versioning for these. The platform on which this is based makes use of Google Firebase as a key components and what used to be called the Google Real-Time API that has been folded into it. React and MaxGraph and TypeScript within the browser with Jest and Selenium for testing. On the back end, Node.js, Express.js, and TypeScript. And then underneath it, a foundation with CatLab, Algebraic Julia, including algebraic rewriting, StockFlow.jl, and Julia. Coming back here, we see a set of model results that include all the stocks associated with all of these models. So not just 4, but the additional stocks IA and V within this composed model. And that's all we have time for today. Thank you so much. And if anyone is interested in exploring potential applications of the incredibly valuable edifice of category theory for public health, healthcare, and community safety and well-being, I'll be delighted to talk with you during our time at this conference. Thanks so much.